In 5.5, when we learned about the collision model, we did look at some graphs. We're going to go a little bit further into those graphs to see how they can be a model for our collision kinetics. So again, remember, everything has to react. It has to collide in order to react. This explains the concentration and temperature dependence of reaction rates. If molecules are constantly colliding, then why do only a small fraction actually produce it? So remember, we have our activation energy. This was first proposed by Svante Arrhenius. And remember, it's at the top of the graph, or it's the height of the peak right here. That is how much activation energy is required to overcome the hump. So remember, it's EA for activation energy. And when you are able to collide and actually have enough energy to react, we create activated complexes, also known as transition states. Exothermic is indicated on this graph, this energy profile graph, by the fact that the products have lower potential energy than the reactant. So if we look up here on this graph, the reactant's value of energy is so high, and then the products, when they're done, have sunken lower than the energy of the reactants. So remember, when it's exothermic, that means that heat has been given out to the surrounding. It's releasing the heat. So the products have less energy because energy has been released. Okay, well, how would it be different for endothermic? In endothermic, the energy of the products would be higher. The energy of the products would be higher because heat is absorbed. Heat has been taken in for that reaction. So the amount of energy that the products are associated with would be higher on the energy profile graph. Also notice the difference in the activation energy, height between the two. When it is an exothermic reaction, there's less activation energy required to have the reaction take place. But when it's endothermic, it has more energy required. So that is just another good thing to see. You might want to draw these yourself in your notes. So to review, the requirements for reactants to collide successfully mean that they have to have enough energy. So the collision energy must equal or exceed the amount of activation energy required. And the relative orientation of reactants must allow formation of any new bonds necessary to produce products. Well, to relate all of this, Svante Arrhenius came up with this equation where K is still the rate constant. So K is still the rate constant that we were talking about in 5.2 and 5.3. K is still a rate constant. A is called the frequency factor for the reaction, and so that would be given to you, probably. And then the e to the negative EA over RT represents the fractions of collisions with sufficient energy to produce a reaction. EA is activation energy, and usually the units for activation energy will be in joules per mole. R is this value of R. If it's joules per mole for activation energy, then we have to pick the R that has joules involved in it. And so the one that we used with gas laws is not correct. We have to use the 8.3145. This R is given to you on the equation sheet, but got to be careful you're using the correct one. Okay, and then temperature, the value for temperature, if you look at the unit on the R value, temperature has to be in Kelvin. So remember, that means you add 273.15 to the Celsius value. Okay. Now, we might not always use this first top equation. Instead, the equation can also be written in linear form. So by thinking about when you take the natural logs to get rid of the e to the x function, that would give us the natural log of K is equal to negative activation energy over R times the inverse of temperature plus the natural log of the frequency factor, A. Okay, so with the linear form, that's really helpful when you're given some experimental data, and we're going to use that in example 8 to help us figure that out. But then sometimes, like in example 9, you might be given 2 temperatures. And remember, the rate constant is temperature dependent, okay? That was something we were told in 5.2. So if there are 2 temperatures, that means there's 2 values of the rate constant for that. And so this would just be a variation if the problem gives you 2 temperatures, all right? So we're going to use this for example 9, but for example 8, we're going to do a graph, so we don't have to do this equation. Okay, so the reaction of dinitrogen pentoxide turning into nitrogen dioxide and oxygen gas was studied at several temperatures, and the following values of the rate constant were obtained at those temperatures. We want to calculate the value of the activation energy for this reaction. Okay, so we're going to need some data. Before I go to a different screen, we will need, remember we said it was y equals mx plus b form when we had that bottom equation from 2 slides ago. So that means that we need to convert the rate constants into the natural log of things. And then the temperatures need to be in Kelvin. And then we need to inverse them for our figuring out the activation energy. And the activation energy is a part of the slope from the equation. So from the equation up above, just look up there, the slope is equal to the negative activation energy over R. So if we can find the slope of this linear function between the natural log of K and the inverse of Kelvin temperature, then we could plug slope in and solve for the activation energy. Okay, so that's our steps of what we will be doing. Okay, so I have plugged everything into a Google Sheet from the table. The E stands for times 10, and you know, on your graphing calculator or on a slightly smarter calculator than mine, you'll see that E. That stands for times 10, okay? But so we need the natural log values of K. So what I'm going to do is I'm going to insert a column to the left, and I'm going to put my natural log values of K here. And again, I will go through class how to do this quickly with you, but for the sake of the video, we're going to go faster. So those are all my natural log values, and then for temperature, we need the temperature in Kelvin before we can inverse it. So I'm just going to have this do it quickly, and we know that if a Kelvin is plus 273.15, so then that will do that for all my temperatures. And then I need to take the inverse of the Kelvin temperature. So I would just have to say 1 divided by and click on my Kelvin temp, and that will produce my inverse values. Okay, so just to prove ourselves that we have a linear function, I'm going to graph the natural log and the inverse of temperature. And we want to make sure that it is a line graph, and we want to use column B as labels. So I go shrink this down. We have a linear function. That's awesome. Okay, I don't know why it doesn't have any axes labels, but that's okay. So this is a linear function, so that tells us that the slope is going to be giving us on our way to figuring out the activation energy. So I'm going to just have it happen in here for the slope, where I need the change in y over the change in x. So the y is, oh, that's fine. Okay. No, that's not right. The natural log values should be the y's, but they are not. Okay, so I've switched it around so that the graph shows that the natural log values are the y-axis and the, let me just put some chart titles on here. Horizontal axis is the inverse in temperature, and the vertical axis is the natural log of K. Okay, so by knowing that, then we need to take the change in ln of K over the change in temperature. So I'm just going to have it do it right here for me. So I'm going to just pick the first two values to solve for this. So that's my change in Y over change in X. And I get negative 1.15 times 10 to the 4th. Okay, so let me go back to PowerPoint. You could have just converted the values instead of graphing it. That would be something to do, or you could linear regression it and find the slope. But so we figured out just now that the slope is negative 1.15 times 10 to the 4th. Okay, and I said before that the slope of this line is equal to the negative activation energy over R. Well, we know what R is, we know what the slope is, so now we can solve for activation energy. Okay, so we will have negative 1.15 times 10 to the positive 4 equals negative activation energy over R. So the two negatives will cancel each other out. And, R is, just look up above on your paper, 8.3145. So activation energy is 95616.75. Okay, and let's report that into significant figures. So we'll have 9.6 times 10 to the positive 4. And then our unit for activation energy is usually joules per mole, with the way that the units cancel each other out. Okay, so again, we had to find the slope, and once we found the slope, then we can just simply find the activation energy. You could have picked any values and not even graphed if you wanted to, but graphing is a good proving factor. Okay, so now example 9, we have this reaction, and at 555 degrees Celsius, the rate constant for this reaction is 1.1 liters per mole times seconds, and at 625 degrees Celsius, the rate constant is 6.4 liters per mole seconds. Using these values, calculate the activation energy for the reaction above. So now we have two temperatures. We have temperature 1 is 550 degrees Celsius, and we have temperature 2 is 625 degrees Celsius. Since we have two temperatures, and we also have two rate constants, because the first rate constant relates to the first temperature, 1.1, and then the second rate constant is for the second temperature, 6.4. That tells me that I'm going to use that second equation that we were given before example 8 that relates both of them, which is the natural log of K2 over K1 equals positive activation energy over R times the inverse of temperature 1 minus the inverse of temperature 2. So we will use that equation to solve for our activation energy this time. Now we need temperatures to be in Kelvin, so T1 in Kelvin is 823.15, and T2 in Kelvin is 898.15. So I'm not going to use those temperatures anymore. Okay, and then also in that equation we have R. Don't forget that R is 8.3145 joules per mole. Kelvin mole, sorry, mole Kelvin, we'll just say that. Okay, so now we just need to plug in and solve it. So I'm going to clear everything on my slide so that I have space to work with. So we have the natural log of 6.4 over 1.1 equals the activation energy over 8.3145 times, now be careful here, the bottom of the first matches, that's T1, so we need 823.15 minus 1 over 898.15. Be careful with your temperatures. Be careful with your temperatures. Okay, so then simplifying, I got the left side to be 1.76099 equals the activation energy, and I just simplified the parentheses, and that was 1.01 times 10 to the negative 4. Okay, and then what I would do first is I would multiply over your 8.3145, and then I would divide over your, be careful with your order of operations, what you're doing here. But the activation energy, when you do that, should be 1.4 times 10 to the 5th joules per mole. So this example was just to show you how, when you have two temperatures, you would use this equation. But if you are just looking at linear data, you would use the other equation.